Hello everyone, I'm Mighty, your hands-on practice assistant. In this session, we'll go through a CFD simulation together step by step and follow along with the practice example. Today's practice example is rotating machinery analysis using the moving reference frame method. In this tutorial, we will use the MRF technique to analyze the airflow generated by a rotating electric fan. So, what is MRF? In reality, the impeller physically rotates, causing the surrounding fluid to rotate as well. However, with the MRF method, the impeller remains stationary while the surrounding air is treated as rotating. For this reason, the computational domain must be divided into two regions, the MRF rotating region and the stationary region. If you want to physically simulate a rotating impeller, you should use the sliding mesh method. Since sliding mesh requires much more computation, the analysis time is significantly longer. By contrast, the MRF method models the airflow inside the MRF region as rotating, allowing much faster simulations. Sliding mesh requires a transient CFD analysis, whereas the MRF method is performed using steady-state CFD. Now, let's see how to create the flow domains for an MRF analysis. First, create a cylindrical region around the fan. Next, create the external flow domain and subtract the cylindrical region from it. As a result, the external flow domain contains a cylindrical cavity. Then subtract the actual fan geometry from the cylindrical region. This leaves an empty space where the fan blades were located. Ultimately, these are the two flow domains required for an MRF analysis. Before we begin the practice, let's briefly summarize the key concepts covered so far. Next, let's take a quick look at the analysis model and boundary conditions. The model consists of an external airflow domain and an MRF rotating domain. The fan model itself is not included in the simulation. Launch NFX and click Open in the upper left corner to create a new project. Go to the Geometry tab, click Import, and load the CAD model. Once the model has been loaded, right-click in the workspace and select Hide All Guides. Now, let's create the air material. We will create both a standard air property and an MRF property. Type Air and click Apply to create a standard air property. Next, type MRF, enable Moving Reference Frame, and click Detailed Definition. Set the rotation direction to the y-axis by entering 0, 1, 0, and specify a rotational speed of 1,000 revolutions per minute. Before generating the mesh, let's define several control seeds to improve the accuracy of the rotating flow calculation. From the Mesh tab, select Control Seed. Select the fan edges inside the MRF region, including the blade thickness edges, for a total of 189 edges. Set the mesh size to 0.005 meter and click Apply. Next, select all circumferential edges of the MRF cylinder, totaling 8 edges. Set the mesh size to 0.01 meter and click Apply. Then, select the 4 edges of the external flow domain closest to the fan. Set the mesh size to 0.05 meter and click Apply. Next, select Linear Grading from the Method menu. Click Select Reversed Objects, then select the 4 long edges of the external flow domain. Set the start length to 0.05 meter and the end length to 0.1 meter, then click Apply. Finally, select the 4 outlet edges and specify an interval length of 0.1 meter. Click OK to complete the control seed setup. Now, let's generate the 3D mesh. First, let's review the mesh generation sequence. Generate the mesh for the MRF region first, followed by the external airflow domain. Now, generate the 3D mesh as shown on the screen. Use an element size of 0.005 meter for the MRF region and 0.1 meter for the external airflow domain. When generating the mesh, be sure to enable Match Adjacent Surface Mesh and Merge Nodes. These options are essential for proper flow calculation across the interface between the two regions. When generating the first mesh, these options are not required. However, they must be enabled when generating the subsequent mesh. Once the mesh generation is complete, use the Clipping Plane tool to verify that the internal mesh has been generated correctly. Now that the mesh is complete, let's apply the boundary conditions as shown on the screen. Follow the video step by step. Also, verify that the number of selected faces matches the example throughout the process. First, apply the MRF rotating wall boundary condition. Select the fan wall surfaces inside the MRF region. Enable wall motion effect control, then click the icon on the right. Click Create and specify the rotation direction and RPM as shown. Return to the wall boundary condition window, select the newly created motion definition, and click OK. Next, apply a wall boundary condition to the bottom surface of the external airflow domain. Then, select pressure under inlet and outlet and assign it to the side surfaces, the top surface, and the surface closest to the fan. Click OK. Next, select outlet under inlet and outlet, assign it to the outlet face, and click OK. Finally, let's define the monitoring conditions. Monitor the average velocity at the outlet face and the average velocity on the MRF interface surface facing the outlet. Let's move on to creating and configuring the analysis case. If you right-click Analysis Case, you can see several predefined analysis types. From here, create a steady-state CFD, then click Edit. You will then see an analysis setup window. Now, let's configure the analysis settings as shown on the screen. Before running the simulation, save the NFX file to your preferred location. Then, right-click the analysis case you created and select Solve to start the simulation. This analysis may take some time to complete, so we will skip ahead and review the results. In the Analysis and Results tree, you can review the solution results for each analysis step. Check the velocity, pressure, and streamline results as shown on the screen. Now, let's review the analysis results obtained from the simulation. Using the MRF method, you can conveniently simulate rotating flow without physically rotating the fan geometry. As shown in the results, you can observe the airflow characteristics generated by a fan rotating at 1,000 revolutions per minute. As you complete today's tutorial, be sure to remember these key takeaways. How was today's lecture? Simulation may seem difficult at first, but if you follow the steps and practice hands-on, you can get started with confidence. With MIDAS NFX, learn the fundamentals one step at a time and challenge yourself with a variety of simulation examples. Then, see you again in the next video. This has been Mighty, your hands-on practice assistant.